So welcome, good morning. We have a lecture number 10. 10 today, we're talking about the balance sense. Just to make sure that people at home hear me, we're trying out the on-site microphone. Just if it doesn't work, please say something via chat, and we'll try to fix that. So balance sense, the picture that you see on the slide, on the first slide, on the title slide, is a picture you have seen before. We already looked at this picture in the context of the cochlea. That was 2 weeks ago. Yes, I will start the slide. We saw this picture before when we talked about the cochlea 2 weeks ago. So we're still in the same location in the body. We're inside this inner ear cavity, but we're looking at the other side, the other half. So share that so the other ones can see it as well. So last week or 2 weeks ago, we looked on the right-hand side at this coiled structure, which is the cochlea. And today we're going to look at the left-hand side, which is three toroidal structures. They're called the semicircular canals. So to start with, I would like to show you a little movie that one former PhD student did. That was actually, he got an MRI of his head, and he was playing around with some tools, and he actually found his own inner ear here. And we're now zooming into the inner ear and into one of the three semicircular canals, and they're filled with fluid. And now it's going over to a CFD simulation where he actually simulated the fluid flow inside one of these semicircular canals, which is induced through motion of the head. And inside the semicircular canal, we will also find hair cells, pretty much the same hair cells as what we had in the cochlea. And these hair cells will be stimulated by the fluid flow. And that creates the sense of motion, the sense of angular motion specifically here in these semicircular canals. And we're going to develop some models to understand what's going on here. And in the second hour, we're going to look at pathologies of these semicircular canals, which are extremely prominent. Its prevalence about 10% is of the elderly population gets these disorders of the semicircular canals. Vertigo is the classical phenomenon. So let's go back to some slides on the basic anatomy. We had this last week, 2 weeks ago already. We are looking only at the blue structure, the ear and the middle ear, the outer ear, the middle ear. They do not really play a role today. It just happens to be located in the same cavity as the cochlea, as the hearing sense. Don't ask me why that is, but it's like that. So if we close in on the inner ear again, just to repeat myself, the inner ear by itself is not a structure by itself, it's a cavity in the bone. So there's all bone around it, and there's something, a cavity inside the bone. On one side, this coil structure, which we know now as the cochlea, and on the left-hand side, we have the so-called vestibular organ or the vestibular system. So the vestibulum is like the whole thing on the left-hand side, and it hosts the balance sense, right? Toward the end of today's lecture, we talk a bit about what problems there could be that the balance sense and the hearing sense are located at the same place anatomically or just next to each other. And moreover, in terms of fluid mechanics, it's interesting that the fluids are communicating with each other, or the fluid spaces are communicating, or essentially it's the same fluid space. We have the perilymphatic and the endolymphatic fluid space that we already had here on the right-hand side with the scala vestibuli, scala tympani, scala media, filled with perilymph or endolymph. And we have exactly the same fluid, and there's a direct connection to the other side. And we see that the semicircular canals are canals which are primarily filled with perilymph, but inside this canal, there's a second canal, a membranous canal, so a thin membrane. And within this membrane, within this membranous tube, tubular duct, is endolymph. So we have again the two fluids. One of the differences in terms of mechanics is that in 2 weeks ago, when we talked about the cochlea, it was mainly the perilymph flow, where we had all like these traveling waves going on. Today, it will be mostly what is happening inside these membranous canals here, which are significantly more slender than the bony canal. So people also talk of the bony labyrinth. They call it the labyrinth because it has so many ways to walk through or to go through, the bony labyrinth and the membranous labyrinth. So the membranous labyrinth is filled with endolymph and it's depicted here in blue. And mainly we will be talking about the membranous labyrinth, or what's going on with the endolymph inside the membranous labyrinth. We also note that there are some red structures here. One here, the third one is hidden back there. So for each of the three semicircular canals, we have one of these red structures. And this is actually where the hair cells are sitting. And then we have two more here. These are called the otolith organs, otoliths. They serve a different function. I'll come to that in a few minutes. And one of them is sitting in this cavity here, which is called the utricle, and one is in the other cavity called the saccule. And everything is connected to everything else. So we'll see that later on a bit more. The whole inner ear, including the vestibular system, is quite an interesting thing also in terms of evolution. You can find this system in essentially all vertebrates. Can find them as far back as dinosaurs. Here on the right, you have the labyrinth of Brachiosaurus, quite large, 5 centimeters large. There are studies which relate the size of the vestibular system, not to the size of the animal, but to the way they move, because the size turns out to be determining like the operating range, in which frequency range the balance sense works well. So it depends a lot on how fast an animal is moving, how nervous it is moving around. And the bigger it is, typically, you can say that the more slowly, the more relaxed the animal is moving around. Okay? So maybe let's first just look at one of these red things here. And mainly I would like to look at the utricle here, or if you like, also the saccular otolith. So the otoliths here, here we have them again. So we're looking at these senses here. These are relatively simple in terms of understanding their mechanics, relatively simple sensors. And fluid mechanics does actually not play that much of a role, but for completeness sake, I would like to introduce them anyways. So these are the linear sensors. So they sense linear motion, right? Or to be a bit more specific, they sense linear acceleration. So one of the most prominent linear accelerations, the one that you feel even though you're sitting, is the gravitational acceleration. So essentially, when you're sitting, they tell you where's up and where's down, right? So how do they work? If you look at one of these otolith organs, either the utricular otolith or the saccular otolith, if you look at one of them, that's what they look schematically. We have hair cells here in the bottom. We have hair cell bundles sticking into a layer, which is we can think of this as a gel, right? Something which can shear, which can move, which has some elastic properties, has a lot of damping. And on top of that, we have little crystals. These crystals are called autoconia. These are calcite crystals, and they're heavier than the fluid, the surrounding endolymph fluid. And this is all immersed in endolymph, okay? So actually their weight, their specific weight is 2.7 times that of the endolymph, or 2.7 times that of water. So what happens if we tilt our head, like that person here on the right-hand side? Well, of course, the autoconia will be pulled down due to gravitational acceleration and will shear this whole gelatinous membrane to the left in that case, and thereby they will tilt the hair cell bundles. That's the whole story. In some sense, this is a simple accelerometer, right? If you were asked to design an accelerometer, you may probably design something which looks like that. Let me put that on the blackboard. So for the otolith organs, they are linear acceleration sensors. And we can think of them as something which looks like that. A simple mass, the mass would be the autoconia, like these little crystals. The spring would be like this gelatinous membrane that can tilt, right? And under the action of acceleration, this can be pulled up or down, right? And will deform this whole structure a little bit. This is actually not complete. If it was only a spring here, there would be quite a bit of well, it would be undamped, and if you stimulate it, it would start oscillating. So this would mean if you tilt your head, it would not just move to the side, but it would actually swing forth and back about its equilibrium state. So what we also need here is a dashpot element or a damping element, right? Not just a spring, but also a damping element. But the important thing is to understand that the stimulation of this sensor is proportional to the acceleration. Right? Why? The force that is pulling this whole thing is equal to m times a. A being the acceleration, could be the gravitational acceleration, it's m times g, but just to be general, it's an acceleration. So this thing here measures acceleration, and you see why I'm stressing this word acceleration so much. Maybe even underline it, because we'll see that the other ones are, the other sensors are velocity sensor and not acceleration sensor, but we'll come to that. So much for the otolith organs. Let's move on to the other part, which actually turns to be way more interesting for fluid mechanics. And these are the semicircular canals. And usually it's sufficient to look just one of the three. Note that these three semicircular canals are oriented in mutually orthogonal positions, right? in planes, mutually orthogonal planes. So each one of these sensors is responsible for angular motion in one of these planes, in their respective plane. So if we have 3 of them, we can sense rotation in all 3 directions, in all 3 dimensions. And since we have 2 of them, there's even some redundancy given. Okay, but for most of what we're going to do, we're just going to look at one of them and assume that we have a rotation in that respective plane. So on the right-hand side, you have a slice through an actual, I think it's even a human semicircular canal. And what you can make out is here, this border here, the outer border, and this is the edge of the bony canal. So this is all filled with perilymph. And inside here, this more slender duct, this bit more darker duct, this is the membranous canal, the membranous labyrinth filled with end lymph. This large thing here is the utricle. The utricle where one of the otoliths is sitting. So the otolith is sitting about here, the otolith organ. So the utricle itself is just a large chamber to which all 3 semicircular canals are connecting, and it also hosts the otolith. So everything is a bit packed up. Then we have this structure here, and this actually refers to this structure here. This is called the ampulla. The ampulla, this widening of the canal is called the ampulla. And it hosts a structure inside here in this picture on the right. You only see half of it, you only see the bottom half of it. The bottom is called the crista. But the main thing here, you don't see, but you see it in this picture, is the so-called cupula. And again, the cupula is a gelatinous membrane, a soft membrane, a very, very soft membrane, actually, turns out, that can deform. So if there's some fluid flow inside these canals, this membrane will deform, right? If fluid is pushing from the left, it will move to the right, and so on. And the deformation of this cupula is sensed by hair cells, which are sitting down here in the crista. So here are the hair cells, and they sense the deflection of the cupula. So if we want to create a sensation, afferents that tell the brain something, we need to deflect the cupula. The more we deflect it, the stronger the sensation. If we deflect to the left, there's a signal that it goes to the left, goes to the right. There's a signal that it goes to the right. Note, please, that the cupula is attached also at the top, not just at the bottom. Actually, it's blocking the whole lumen of the canal. And this is often misunderstood. And I would like to go to this picture here, which shows actually 2 images that I took from, well, somewhere on the web where I found them. The one on the left actually shows exactly the picture it is as it is. We have the cupula, which is tightly attached. If we have fluid flow from the right, obviously it has to move to the left, right? It cannot go anywhere else. This picture on the right shows a slightly different situation where the cupula is not attached. Still, if there's fluid flow from the right, it will move to the left. But the reason why this structure here is moving to the left is a different one, right? It's being pushed essentially by viscous forces, or let's say by drag forces that are pushing this whole structure to the left. For this, you need quite a bit of flow. For this here, this is essentially just a matter of mass conservation while it's moving to the left. And it turns out that that thing on the right is completely wrong. And that thing on the left is right, is right. Yeah, just to make it clear. By the way, if it was like the one on the left, there are actually diseases where you have a rupture in the cupula like separates from the top side, and then the semicircular canal stops working. they would be more working like acceleration sensors here, whereas this structure here, this makes the semicircular canal a velocity sensor, a velocity and not an acceleration sensor. But let's do a little experiment next, which should give you a bit of an idea what's going on. All of you who are, yes? Well, I mean, this is just not how it is. This is all wrong. This is right. Okay. So I would all of you, including people at home, please take something to read, something where something is written on it, piece of paper, take it in front of you and start reading it, right? Or I mean, obviously you can read, you don't have to test that. Now you start moving your head up and down about that speed, at that frequency. And try to see if you can still read. And I'm pretty sure all of you can still read, even though your head is going up and down relatively fast. Okay? So apparently your eyes are compensating automatically for the head motion, or doing the opposite, right? It's a vision stabilization system. Now let's do the same thing, or the opposite thing. Instead of moving our head up and down at that speed, we move the paper up and down at that speed. Can you still read it? Yeah, hard or even impossible. So what has happened? The relative velocity is always the same, right? Why were we able to fix our gaze onto the writing when we move our head, and why not when we move our hands? Well, the reason is that when we move our head, we stimulate the semicircular canals. And the semicircular canals, they are directly connected via brainstem to the eyes, to the eye muscles. And this is known as the vestibulo-ocular reflex. And this happens to be, this happens to be the fastest human reflex. It's reacting in less than 10 milliseconds. It's really fast. It's involuntary, it's a reflex, right? And it's an almost direct connection from the semicircular canals by a few neurons directly to the muscles of the eye. And it's wired in a way, like it's crossover wired, such that when I tilt my head up, my eyes will involuntarily move down and vice versa. There's also torsional VOR, there's this VOR and this VOR, okay? 3 axes, 3 semicircular canals. And now we come back to the story about velocity sensors. So apparently, when I move my head with an angular velocity of, let's say, 10 degrees per second or 20 degrees per second, the eyes have to move with -10, -20 degrees per second, okay? We need the velocity as information, not the acceleration as sensor. Another thing, and we will see this especially in the second hour, this sense here is used by doctors to diagnose the function of the semicircular canals. Because it's a reflex, if the semicircular canal works, you will see the eyes moving. And you can pretty much take the velocity of the eye motion, and you can have eye trackers. You can take the velocity of the eye motion and say, well, this obviously is what the semicircular canals are sensing. So it's a very, very important reflex. And I can show you some examples here. These are 3 diseases. One is the top shelf vertigo. We're going to look at that later on. So on the top left in the green inset, you see he moved the patient up and down, and maybe it's a bit difficult to see now, but you see now the flickering of the eyes up and down. So this patient has a sensation of motion, even though there is no motion. We'll come back to that. Let's maybe go to this one. That's an interesting one. It's called the Hennebert sign. So the doctor is pushing onto the ears, right? Just pushing like this. and the eyes start flickering, right? Okay. So what has happened to a person whenever the doctor pushes onto the ears, that person has a sensation of spinning like that, and that's why the eyes are flickering. And the third one is Tullio's phenomenon. I'm not sure if you can hear it, if you can also hear it at home, but there's a beeping noise, and it's a bit difficult to see, but the eyes actually make a torsional movement. You can see maybe if you look here at the this blood vessel. The eye is torsionally compensating in time. So what does that mean? That person, whenever that person hears a sound, it feels like they're tilting this way. So that's why the eyes are trying to compensate in a torsional mode. So there's quite a lot of diseases connected to that, especially one on the left. The top shaft vertigo is extremely prominent, mainly in elderly people. And that's really why it makes a lot of sense to study that. Oops. So let's go on. So let's go over to fluid mechanics. How can we understand what's going on here? And first of all, I would like to go through schematically through this whole thing, and mainly what we're trying to answer here, how can it be that this thing is sensing velocity and not acceleration? How does it sense the velocity? And we simplify, for that matter, the whole semicircular canal to a torus, toroidal structure. And on the top in red, you have this little cupola here. I showed in a deflected mode. And we have some flow here in this direction, which we call V dot, volume dot, or sometimes like in blood flow, we used to call it a Q, a volumetric flow rate. And we have here a volume V, and by the volume V, I mean the volume, how much the cupola has been displaced. Essentially, it's the volume under the cupola, right? And what is this in the middle? This is alpha dot dot. So alpha would be like the angle with which I define my head position, right? And alpha dot is the velocity, the angular velocity, and alpha dot dot is the acceleration. So when I start moving my head, I obviously accelerate the head, and when I stop, I decelerate it. So it's a pattern of acceleration and deceleration. And then in the first place, this acceleration will lead to a fluid flow. It's simply the inertia of the fluid, right? If you think of a bucket with water and you start accelerating it, of course, you will get some fluid motion inside there, right? And this fluid motion is directly proportional to the acceleration, okay? So V dot, the amount of fluid flow to first order, this is all like a first order model, to first order is proportional to the acceleration, right? The more we accelerate, the more fluid flow we have inside the semicircular canal. Now comes the cupola. And the cupola, because it is blocked, because it's blocking, it's not blocked, it's blocking, the whole semicircular canal has the role of an integrator. The displacement of cupola is essentially the integral over this volume flow, right? Whatever velocity you have, if you have like let's say 1 micrometer of fluid, 1 micrometer per second fluid flow velocity, and you flow for 10 seconds, you get a displacement by 10 micrometers, okay? And if you have a deceleration, so the fluid flow is going the opposite direction, the cupola will move back, but according to the integral over time of the fluid flow. So the cupola, and this is why I stressed so much that it's attached on either side, that's really completely blocking the flow. The cupola creates an integral of the endolymph flow, and well, it's essentially displacement is proportional to the integral of the flow. And this is obviously and also proportional not to the acceleration, but proportional to the velocity. So this is sort of the story behind why semicircular canals are velocity sensors and not acceleration sensors. We can start to become a bit more, let's say, more physical, doing a bit more physics, and develop the first ever model for semicircular canals. This was due to Steinhausen, who published that in 1933. And what was the idea of Steinhausen? Well, Steinhausen essentially postulated the formula that we have here at the bottom. Steinhausen postulated that the semicircular canal can be modeled as an oscillator. As an oscillator which can be described by second order differential equation. If V again is here, this volume under the cupola, like how much the cupola is displaced, V dot second derivative. This has something to do with acceleration. This has something to do with velocity, and this has something to do with the displacement itself. Okay. So where do these terms come from? Well, the first term comes from this formula here. So this is really the basic, think of like Newton's second law, force equals mass times acceleration. So the mass, that would be the mass of the whole fluid and the whole canal. And we start moving that whole system. We start moving it with an acceleration alpha dot dot. And the volume inside this whole canal is VSCC. So it's like the volume, the fluid volume of the whole canal. So this is sort of the force that is felt by the system, or that has to be put onto the system by accelerating the whole system. On top of that, it's not just the whole system that is rotating, it may also be a fluid flow relative to the canal. So we move the whole head, like the whole canal, the bony structure, and inside the bony structure, there may even be a flow on top of the head motion. So this is like the moving head, and this is like the fluid flow, the flow of the end length. So these are the two terms, and the mv dot dot then goes here, and this here will go to the right-hand side. I lumped this here by parameter kappa. Then another force that is acting here is the viscous drag, right? It's a viscous fluid. We have a very slender canal. It's maybe a Poiseuille-like flow inside this canal. It's probably low Reynolds number, or it is low Reynolds number. So we probably could even estimate what this R is, right, through the Poiseuille law. But apart from determining R, we can just say the drag created by this fluid flow is equal to a drag coefficient R times the velocity of the fluid V dot. And finally, we need a force from the cupola. We have not yet talked about what the cupola is doing. The cupola is an elastic structure, right? And if we are displacing it, it's pushing back. It's like the spring. It's similar to the spring that we had in the otolith organ, okay? So if we push the cupola in, it wants to push back. So this is like this elastic force, which is proportional to the volumetric displacement. So we have these three forces, and of course the sum of the three forces should be a balance, should be zero. So if we add all of them up, we end up with this equation here. This is Steinhausen's model. Okay. So I'm sure you have all solved such equations before. It's a second order constant coefficient, ordinary differential equation. Inhomogeneous is driven here on the right-hand side, but this is a relatively standard problem in mechanics and dynamics. So let's look at what we can learn about this system. Let's maybe first just look at the characteristics. Forget about the right-hand side for now. Just the left-hand side. This is an oscillator, right? Mass M, damping R, stiffness K. And we know that these oscillators, they have certain resonance frequencies. They can be overdamped, can be underdamped, and so on. The way we analyze that is typically by making a sensible ansatz, like that one here, an exponential ansatz that always works with constant coefficient, ODEs, linear ODEs. And we have here this parameter sigma in it. We can interpret this as an eigenvalue of the system. And if we plug in this ansatz here into this formula, you see from the dot dot, we get a sigma squared here. And from the V dot, we just get a sigma, and here we get nothing down. And we can then solve it for the sigma, and we see that there are typically, or not typically, there are two solutions for the sigma, right? Depending on the values for R, for M, and for K. So I'll just standard way of solving constant coefficient differential equations. Now, let's do a special case first. What is happening if we assume an oscillator without damping? So R would be 0. Huh? Let's just forget about R. If R is 0, the first term goes away, this term goes away, and all that remains is a minus K over M. Okay, square root of minus K over M, obviously that will become a imaginary number, so it's I square root Km, because square root, there's a plus and a minus solution. So there's, for the case where R happens to be 0 and a system without any damping, we would get an eigenvalue here. Here, this is the complex plane for sigma, one here and the other one here at the bottom. A pair of complex conjugate eigenvalues. What does that mean if we stick in an imaginary value here in our answer? If sigma is a complex valued number, well, then we have e to the I something t, and that's an oscillator. So this is the simple case where we have an undamped oscillator, and square root of K over M is just the resonance or the eigenfrequency of the oscillator. Stiffness divided by mass, square root thereof is the eigenfrequency of any oscillator. This is all standard stuff that you maybe did even before, well, a few years ago. If you start increasing the damping, and I showed this here on this curve, so here we start at R0, no damping, and if we start increasing the damping, the eigenvalues will move to the left on the complex plane. The locus of the eigenvalues will move to the left. What does that mean in the solution? It means it has a real part, a negative real part, which creates exponential decay. That's exactly what damping is doing. At the same time, the imaginary part decreases, so the eigenfrequencies are decreasing. And there's like a critical point here where the two eigenvalues are meeting on the real half plane. So we have only real valued eigenvalues. So nothing is oscillating anymore, it's only damped. And if we increase the damping even further, the two eigenvalues separate again and move. One here moves close to the origin. It never becomes positive, it's always negative. And the other one moves farther toward infinity. This situation here, when we're on this line, no more oscillation, this is a situation that's called an overdamped pendulum. A pendulum with supercritical damping. It's a pendulum that does not oscillate anymore. You can think of this if you have a pendulum with a mass under it. If you like fix the screw that holds the pendulum, like fixed a bit more, so you get a lot of friction, it will not swing anymore. It will just slowly move toward its equilibrium position. This is an overdamped pendulum. Okay. So also the semicircular canals seem to work like a pendulum like an oscillator. And the question is it an overdamped pendulum or like a classical oscillator with an eigenfrequency? So essentially, this is summarizing again what I just said. No damping with a classical oscillator. Supercritical damping, large damping. We have two eigenvalues with different damping rates. Now, the solution is the semicircular canals are like overdamped oscillators, or an overdamped oscillator, overdamped pendulum. Why? If it was underdamped, subcritically damped, we would first of all have oscillations, which is not really a good thing, because it will, well, would not help you to fix your vision and to keep stability. Plus, if you have a little damping, we have very long transient. So if you stimulate the system, it keeps swinging for a long time, right? And you don't want that. You want accurate information in time. If you start moving, you want the information. If you stop moving, the signal should go away. So having an underdamped oscillator is not a good thing. Having an overdamped oscillator is a good thing. So this is a situation we have in a semicircular canal. And we can reach this situation by having a large R, a large damping. And where does this damping come from? The damping comes from fluid viscosity. And we're in a small, slender duct. So having small, slender ducts inside the inner ear is not just a size thing to make it small and to make it fit somewhere. It's also small because small tubes have huge or high, very high damping, right? Viscous flow through a small tube has more damping than through a large tube. So there's also a good mechanical reason why these tubes are so small. Another way we can interpret these two eigenvalues are as timescales. Let me look again at the ansatz. So sigma, the eigenvalue sigma, stands in front of a t. So 1 over t, 1 over sigma is something like a characteristic timescale. Okay, so let's try to understand these two eigenvalues here as timescale. We have plotted that here. 1 over sigma. So there's the sigma plus and sigma minus. These are the two different eigenvalues. And we see that one of these timescales is like R, the damping, which we know is large, divided by K. And K is the stiffness of the cupola. And I told you a few minutes ago, the cupola is very soft. So K is small and R is large. So this is a rather large timescale. And because it's dominated also by the stiffness of the cupola, this is typically called the cupola timescale. If you put in the right numbers, it turns out to be on the order of let's say 10 to 30 seconds. This is the time it takes for the signal to decay. I'll come back to that, what that means. The second eigenvalue, 1 over sigma plus, can be written or approximated by m over r. So this has the mass in it and the large damping. The mass is small, it's a tiny little object. The damping is large, so this is a very small number. This number turns out to be on the order of about 10 milliseconds. Okay, maybe you remember 10 milliseconds. That was the speed of the reflex. Okay, so these are two timescales which are determining. These are like corner frequencies or corner timescales. Everything that is faster than the viscous timescale is too fast to be sensed. The system needs a reaction time, and the reaction time is given by this TV. That one here is like a maximum timescale. Everything that takes longer than that is difficult to sense. If you do the whole analysis of the Steinhausen model in frequency space, maybe you have seen this like in control theory, you can do these Bode diagrams. I can show that the transfer function going from the velocity the angular velocity of the head to the cupola displacement can be written like that. So this is the transfer function. S is like this frequency coming from the Laplace transform. And if you plot this over different frequencies, you see that we have a relatively constant gain between the two corner frequencies. And these two corner frequencies are given by 1 over Tc, 1 over Tv, or sigma plus and sigma minus. Anything that goes faster, very high frequency stimulation, it's blocked. We call this a viscous blocking. I'll come back to that later on. Everything that's slower, the signal drops off. This is what we call a mechanical adaptation. To clarify what this all means, I show you this picture and then we take a break. But I would like to go through this first. Let us assume we have a motion pattern like shown here in green. This is the angular velocity of the head. So first we are at rest, and then we have a rather sudden acceleration, and we go to a constant velocity, and then we stop again. Huh? So we're accelerating, moving, stopping. Okay, so it's like a typical motion you could do. How does the system, how does the Steinhausen system react to it? Well, first, I told you there's the viscous time scale which determines how fast the system can react. And this is this here, this TV. This is what the cupola will be doing. The cupola takes some time to react, and that time scales like this TV. And when you stop, the opposite is happening, but it takes, again, a time TV to react. What happens in between here? So here we have a constant velocity, but the signals or the deflection of the cupola slowly decays. Why is that? Okay, so the cupola has been displaced. We're in a situation where we're just rotating our head at a constant velocity, but the cupola, which is an elastic thing, it's pushing back. It's slowly, slowly pushing back. Okay, and that's exactly what we see. And when the deceleration comes, it decelerates, but there's an overshoot to the opposite side. Why? Well, the deceleration will lead to a shift in the cupola position by as much as we decelerate, but because it has relaxed before, it will be shifted to the opposite side by the same amount. And again, it will take some time to relax, okay? And I'm sure you have played with this. Maybe you don't do it anymore today, but as a child, I'm sure you did it, right? Did you ever do this spinning game, right? Spin around, or maybe ask your colleague to do that 10 times? Or sit on an office chair, right? And keep spinning the office chair for quite some time. So if we keep spinning it, that means there's no more acceleration. We have a constant angular velocity. So we're like on this flat thing here. During the spinning, a constant velocity on the office chair, can try it out afterward. After maybe 10, 20, 30 seconds, the sensation of spinning wears off, right? Your system adapts, has a mechanical adaptation, the cupola relaxes over that time. And after, well, let's say after 1 minute, everyone will have lost the sensation of spinning, even though you're still sitting on a spinning chair. And if then all of a sudden you stop, you ask the person, what do you feel now? And the person will tell you, I feel like I'm spinning the opposite way. And that's exactly this. You feel like you're going the opposite way. Huh? And if you then ask the person to open their eyes, you will see the eyes flickering. Okay, because the eyes, the VOR, is generating a signal, hey, I'm moving, and the eyes will try to compensate. And because then what you see and what your head thinks is not matching, that's what gets you nausea, right? Okay, so this is the basic function of the semicircular canal. So I think we should take a break here. Let's meet again at 15 past, then we'll continue with that. All right, So let us continue. Maybe one or two more words about this slide. Maybe it's something confusing. The decay that you see here, this relatively, hold on, by the laser pointer. Yeah, this relatively slow decay. I mean, I'm showing this here because, well, this is how I plotted it. In reality, in most practical motions that you do, they are over so quick, right? I mean, when you move your head, it takes less than a second. So these motion patterns are usually done within a second. And during such a short motion, you would not see this decay that much, right? Decay of that magnitude, you would only see if, for instance, you sit on an office chair, keep spinning for 20, 30 seconds, okay? Which I hope you don't do all the time, right? So most of the time, what you would see is that this is a rather flat curve, right? So apart from this short reaction time, the red curve would pretty exactly reflect the green curve. Only if this motion persists or remains constant for a long time, and long talking about 20, 30 seconds, then we start seeing this significant decay, and at the end, the overshoot to the opposite side. Good. So this was all Steinhausen's model. And we see that it already gave us quite a good idea, and we could use some mechanics to it. But of course, it would be nice to get a bit better handle on all these numbers. And to that end, we should go and start working with our classical equations, with the Navier-Stokes equations, for instance, to really get an understanding of what's going on. And I don't want to go into too much detail, but the lecture notes, they should have all these derivations to it, or also some references to read more. Essentially, what we do here is that we consider this whole canal to be a pipe, like a pipe flow, because the curvature is relatively small. According, like when we think of Dean vortices, we can consider this also as just a straight tube, or the curvature doesn't really matter that much for the fluid flow. And we can formulate like an axial momentum balance along the main axis of the canal. And this is essentially what we have here. Momentum equation. You may recognize part of it from the Navier-Stokes equation. On steady term on the left-hand side, the pressure gradient, we need to talk about that later on, and the viscous term here. Why do we have here the U plus A dot R? Well, that is because we are dealing in a moving coordinate system. So we consider ourselves sitting on the head or moving with the head. So we're always moving with the whole system. And we only see the velocities of the fluid relative to the head, so relative to the bone. And this is the fluid velocity U. And in the inertial system, of course, we need to also reflect the motion of the head. So this is the head motion. The velocity of the head, alpha dot, the angular velocity times r, the major radius r. So this is like the velocity of the canal due to the head motion plus u, and that's the fluid velocity. Okay. And of course, the same goes also here in the viscous term. Now, since this is a constant, Laplacian of that gives 0, right? So we can drop that term here in the Laplacian. For now, this is really, there's no physics behind this. Just for simplicity, because we want to talk about this later, we just forget about the pressure gradient for a second. And we consider a steady situation. This is really just trying to get a balance. So we ask the question, if we have a certain acceleration of the head, why is an acceleration? Here's alpha dot, but here we have a ddt. If we have a certain acceleration, this will end up rho alpha dot dot times r. And if we try to balance it against the viscous friction, how much flow can we generate? If we move a canal what is the flow velocity which creates just enough friction to compensate for the stimuli by the acceleration. So that's what we get when we balance these two terms here, this term on the left-hand side and this term on the right-hand side. And if we assume for U a Poiseuille profile, just an assumption, then we can actually calculate what a Laplacian is. And we obtain an algebraic term for the viscous damping. And this is essentially what I did down here. And if you had this like the amplitude or the maximum velocity inside the canal, we can see that we reach velocities, well, according to this formula here, here's the alpha dot dot coming from this term, the R, and here this A square. A is the radius of the slender canal, and nu is the viscosity of the endolymph. We get this formula here, and if we plug in here reasonable numbers, and by reasonable I mean angular accelerations that we typically have in our daily lives, then we reach velocities of 10 to the minus 4 to 10 to the minus 5 meters per second. So that's about a 1/10 of a millimeter to a 100th of a millimeter per second, or 10 to 100 microns per second. So if we move our head, the velocities in there are small. They're really small, huh? But they're there. They're non-zero, and it will lead to a Poiseuille flow. A very slow Poiseuille flow will lead to a Poiseuille flow. And because the canal is so slender, the canal is only about 0.3 millimeters wide, or 0.3 millimeters wide. It will lead to a lot of friction, viscous friction, which balances the inertial force. If we use this velocity and compute a Reynolds number, a reasonable Reynolds number for this pipe, we see the Reynolds number in this pipe is 10 to the minus 2 to the 10 to the minus 3, which is definitely Stokes flow. The assumption of a Poiseuille flow is definitely a good assumption. This definitely will have the shape of a Poiseuille flow, very slow Poiseuille flow. So this was for a steady case. Now, if we use the same equation, but now we ask for the unsteadiness, how fast can the system adapt? So we take this term here, the unsteadiness, how fast can this velocity, how fast can this velocity build up if we start accelerating? And if we do this balance again, we end up with a term which looks like a square over nu. And we actually start seeing that we're getting exactly in this range of these 10 milliseconds, or here's 20 milliseconds, but we're really getting into the range of the reaction time of this reflex. And if we look at this a square over nu, and here we have a time scale, and if we bring it to the left-hand side, we have 1 over time, which is like a frequency. We start realizing that this looks a little, this term here, or this formula here, looks a little bit like a Womersley number, okay? Right, or Womersley number squared. If we square this, we have an a square, like here. We have a nu, okay? And we have a frequency on top, and if we bring the frequency to the left-hand side, we get a time scale. So this viscous time scale, what is this? This is actually a place where the Womersley number inside the semicircular canal is 1, okay? And anything that goes faster than this time scale, the Womersley number inside the semicircular canal is beyond 1. And we start getting all these funny effects of a Womersley profile. And this is exactly where the semicircular canal stopped working. This is why this limiting time scale, TV, has a lot to do with Womersley flow. A well-operating semicircular canal is in a regime which is at low Womersley numbers, Womersley 1 and below. As soon as the Womersley number inside the semicircular canal goes above 1, it stops working properly. So this is what we can just derive by doing a simple balancing of terms in the momentum equation here. But I did not yet explain to you where this pressure gradient is coming from. So we have a toroidal canal. And if this toroidal canal was just an open torus, well, there should not really be a pressure gradient, right? Because you can go on infinity. If the pressure is decreasing in one direction, well, you will come back. Once you go once around, you come back to the same location, and then you would have a pressure jump, right? So it's kind of weird. Well, it's only weird if we neglect the cupola. If we consider the cupola, we see that the cupola is actually creating a pressure jump, right? The deflection of the cupola makes sure that on one side of the cupola, the pressure is higher than on the other side. This is what is deflecting the cupola. And this pressure difference is reflected in a pressure gradient along the canal. So we can actually consider or can start modeling a reaction force of the cupola, V, the volume under the cupola, times the spring force K, that's what we have in the Steisenhausen model, leads to a force F. If we divide this force by the cross-section of the canal, we get a pressure. And if we distribute this pressure along the whole length of the canal, we get a pressure gradient. And this is a pressure gradient which is pushing the flow, actually pushing the flow back, right? This is usually opposing the angular acceleration. It's the mechanical adaptation. How do we get the volume under the cupola? Well, we take the velocity, and since we assume a Poiseuille profile, we can assume axisymmetric flow. So this is the volume flow rate, or the V dot, or Q of t. If we integrate over time, we get the volumetric displacement under the cupola. And if we put all of this together, or actually someone else did this, we end up with the model of Van Buskirk that was published in 1976. This is essentially the momentum balance, or Navier-Stokes equation, if you wish, for a semicircular canal. Has an acceleration of the fluid flow in it. It has the angular acceleration of the head in it. This is what is driving the system. This here, this double integral here, this exactly the volume under the cupola times an epsilon. Epsilon in that case is like the a parameter for the stiffness of the cupola. And back here, we have the viscous term, right, with a Laplacian in polar coordinates. So this term here actually corresponds to the mass times velocity v dot dot, right? This acceleration term of the fluid. This term here is the viscous term, right, in Steinhausen's model. This double integral with epsilon is like the cupola reaction force. And finally, this term here in Van Buskirk's model corresponds to the driving force. We can also analyze now the Van Buskirk model. We can look at eigenvalues. I don't want to go into details on that, too many details, but we still find the same eigenfrequencies or eigenvalues. They're a bit ordered in a different way, but they essentially mean the same thing. We have the cupola mode. We have now many duct modes, but the first one actually corresponds to what we have called the viscous timescale, right? The cupola timescale and the viscous timescale. And the cool thing now is that we get actual expressions, we get real numbers for it, which are not based on this, let's say, phenomenological Steinhausen model, but which are based on the actual model using Navier-Stokes. So we can describe the cupola timescale by this formula. K is the stiffness of the cupola, R is the size of the canal, A is the radius of the slender duct, mu is the viscosity, beta is a geometrical parameter. And again, we have the viscous timescale, which comes out nicely as A over nu. this is where this all came from. And this again defines us the operating range. Important information, I think you will look into this in the homework assignment. The small canal lumen, the slender size of that, so that's A. Look here, it stands in the denominator. So the smaller the canal is, the larger TC is, or the smaller this corner frequency is, and the smaller A is here, the more this moves to the right. So a small canal makes a larger operating range. This is one explanation why semicircular canals are so small. Let us spend the last 30 minutes now on pathologies of the vestibular system. And I would like to show to you again this movie here. Oops. This is, yeah. Maybe I tell you first what you will see. On the top left, you have a little inset. Maybe look at this one first, the green bordered inset. You see the doctor taking a patient who's sitting on a bed, and he's taking the patient and putting the patient is sitting upright, and he's putting the patient in a supine position. So the patient is lying down. So this is the initial movement. The initial movement, which should be sensed by the semicircular canal and will lead to an eye motion by the patient. This is all normal, but you will see later on is that when a patient is in supine position, the eyes will start flickering again, and that's the pathology. Okay. Sorry. Okay, now look at the eye. The patient is at rest now. I see how the eyes are going up and down. This is called beating. So the speed with which the eyes are now moving up and down, this is roughly the speed that the person is perceiving. So that person really feels like it's spinning around dramatically. Eh? Even though you see top left, the person is perfectly at rest. And now it's over, huh? Maybe let's run it again. Okay, patient upright, now lying down, and now it stopped, nothing happens, and now it starts. Okay. So this is very typical for this disease. You have a motion to stimulate the whole system, then maybe for 1 or 2 seconds, everything seems okay. But 1 or 2 seconds later, all of a sudden, the person feels like it's spinning again. Quite dramatic. This is really a problem for these people. This is called top shelf vertigo. Top shelf vertigo, why? You're trying to pick up something from the top shelf, so you're tilting your head back, picking it up, and 1 or 2 seconds later, you start falling over, okay? That's why it's called top shelf vertigo. Top shelf vertigo, you see here on the schematic on the left, what the doctor just did. There are animal experiments, in vitro and analytical models, and I would like to show you a little animation of an analytical model. And what do we see here? So we see the semicircular canal, or at least a part of it, and in red again, the cupola, and we see how the cupola is deflecting. And we see that during the motion like now, the cupola is deflected a lot, as it should, right? That's what it's there for. But we see that after the motion, the cupola is deflecting again. Now, okay? And we see this here on the right-hand side in this diagram. The green line is really the velocity of the head. So we're accelerating, going to high velocity and slowing down again. Everything done like in 1 to 2 seconds, and then the patient is lying at rest. And red is what the cupola is doing. First, it's following nicely what the head velocity is doing. There's a little overshoot the opposite side, and after a little latency time, it deflects again. Why is it doing that? Well, It's doing this because this blue thing here, or because of the little particles also shown. Oh, sorry, I need to put the laser pointer. Because of this blue thing here in this model, or the little particles shown here. There are little particles in a semicircular canal. They should not be there, right? Hopefully all of you do not have these particles in there, but they can go in there due to trauma, for instance, or age. You can have little particles in there, and these particles are falling down. They float. Well, they don't really float. They fall through the fluid, and they generate a flow. Falling particles, if you have something trickling through fluid, it drags along fluid and creates a secondary flow. And this secondary flow deflects the cupola a second time. This is top shelf vertigo. There are clinical experiments being done, so you can really study this in a very controlled manner. This is like this rotating chair they have at the Unispital across the street. Again, this is a typical measurement from a patient, the initiating movement, then a short latency time of 1 to 2 seconds, and then it kicks off. And it's very classical, or it's actually normal, that the symptoms or the perception of the patient is in the same direction as the initial movement. We call this here nystagmus velocity. I have not defined this name yet. Nystagmus is actually what we call this compensating eye motion. So it's like the velocity of the eye in the slow direction, right? And we see here the velocity of the eye is here roughly at 60 degrees per second. So this is what the brain, or not the brain, what the semicircular canals think the person is doing. Think it's moving at 60 degrees per second, which is quite fast. So summarize that. What is top shelf vertigo? By the way, the medical name is benign paroxysmal positional vertigo, BPPV. Or in German, Lagerungsschwindel, occurs in 9% of people over 70 years. Most common cause of vertigo. Really, it's the most common cause in the world. Leads to dizziness, nausea, imbalance, obvious. And this is now the interesting thing in terms of mechanics. Vertigo attacks are triggered by a specific angular movement of the head, right? Like lying down in bed or picking up something on the shelf. There's always a short, well, not always, but there's mostly a short latency after the triggering motion maneuver of a few seconds. And then the actual vertigo is in the same direction as the preceding head movement. There's typically a peak after 5 to 15 seconds, and then it slowly wears off. It wears off and lasts maybe up to 30 seconds, maybe some even more. We know it's a mechanical problem. There's also other kinds of vertigo, which can be, for instance, be caused by stroke, right? But this type of vertigo, which happens to be the most common form, is a purely mechanical problem of the semicircular canal, and is caused by these particles. These particles are floating freely in the semicircular canals. The problem for medical doctors is that they cannot see these particles. Why? First of all, they're really small, 5 to 30 microns, we think. And they're inside the inner ear, right? You cannot really access that. Imaging systems like X-ray, you cannot see it on that size. So there are 6 semicircular canals, 3 on either side. And you have a person that tells you it has vertigo, and well, where is it? Where are these particles now? How many are there? Are there one? Is there one big one, 10 small ones? Who knows? If they know where the particles are, there are specific maneuvers that trained doctors can do with a patient. And essentially what they're trying to do is to shake out these particles out of the canal, that they fall back into this larger cavity, the utricle. This is the idea. They only hurt, or they only create vertigo as long as they're in the slender duct, because they take up a certain part of the lumen. They have some blockage, create fluid flow. I'd like to show you this here. This is a numerical simulation of such semicircular canal. You see, it's not perfectly toroidal. This is an actual patient case. This dot here is a particle, and no, it doesn't work like that. And now the patient is turned, and you see the particle falling down, sometimes hitting the inner wall, sometimes hitting the outer wall. It settles at the lowest point. So this typically, when the vertigo starts wearing off, it still takes some time, right? So again, the cupola relaxation time. And when a patient is sitting up again, it all comes again, but the opposite direction. So you see, it's in terms of fluid mechanics, quite complex because you have this fluid particle interaction. And this is only with one particle. If you do the same simulation with many particles, it becomes even more complicated. So hence, it would be nice to create some kind of a model for that. We attempted to do that by just keeping, let's say, the physics as simple as possible. We assumed a particle somewhere inside this canal at a certain position under the action of gravity. Because gravity is really what moves these particles. Gravity pulls them down. This is the density difference between the density of the endolymph and the density of the particle. I told you these particles, oh yeah, I haven't told you that. These particles, by the way, they are the otoconia particles. Maybe you remember them. These are the particles that are actually in normal condition. These particles here. So these particles, they are sticking on this surface of the otolith organs, right? And these otolith organs are sitting here in the utricle. Now, if you have an accident, a trauma, head trauma, like you hit your head, these particles can fall off, right? Or by age, the whole structure can degenerate and the particles can fall off. And then they're somewhere sitting here, as long as they're still in this utricle, they do not really hurt. But due to some kind of motions, they may fall into one of these canals, and then the problem starts. Okay, so we know where these particles originally come from. They're these otoconia, and they're 2.7 times heavier than endolymph. So we can compute the gravitational force felt by these particles, and of course we need to project it onto the axis of the canal. So this is sort of this gravitational force in the direction of the canal. Then we have to add some friction, some drag of these particles, right? They have a certain size. We're in a Stokes regime. And for particles in Stokes flow, in a low Reynolds number flow, we have a formula. This is called the Stokes formula. This is a formula which gives us the drag force of a particle as 6 pi times nu, viscosity of the fluid, times rho, times the cross section, or the radius of the particle, times the velocity. What is this? So x p dot is like the velocity of the particle, and u p is the velocity of the fluid at the position where the particle is. If the particle is in the center of the canal, the felt velocity is higher. If it's at the edge, the velocity goes to 0. So this is the relative velocity between particle and fluid, which leads to a drag force, a Stokes drag force. And we can add all that into the von Buskirk model. And then we get this huge, ugly equation. It's an extension of the von Buskirk model in red. These are the terms from von Buskirk, and everything else comes from the particle. Let's look at the bottom first, bottom line. This is the equation for the particle. And this is the acceleration of the particle, position of the particle, second derivative is the acceleration. We have the position of the head. This here is the Stokes drag. It's all written here in dimensionless parameters. And the third term here is gravitational force. So in some sense, it's again, it's like it's a second order OD, and we have a second derivative here for the position, a first derivative for the velocity, and this here, if we linearize the sign, it's like a reaction force. So this is what the particle is doing. And we have one additional term in the van Boskirk equation, which is essentially the negative of that, right? Why? If the particle feels drag due to Aktio et Reaktio, the fluid feels the drag as well in the opposite direction, right? Whatever drag the particle feels, that's the force the particle exerts on the fluid. And this is exactly the force that drives the flow. This is additional, the secondary flow driving force. We can analyze these equations. I don't want to go into any detail. We can linearize the particle model. We see again, it's a second order OD. We can look again at different values for these non-dimensional numbers. And we find again that it has the character of an overdamped oscillator. So we have now like two coupled oscillators. One is the particle falling down and one is the fluid moving with the cupola. And both behave like overdamped oscillators and both have these eigenvalues. And if we analyze these eigenvalues, we find that there's a slow particle mode, which essentially is the mode, the eigenfunction, which tells us how fast the particle is falling down. It tells us that time is the time scale with which the particle settles in the canal. And that happens to be very close to the original cupola mode. And whenever two eigenvalues are close together into a system, in a coupled system, something interesting is happening. And that's exactly sort of the mathematical explanation for what is going on in top shelf vertigo. We have the cupola time scale right here. The cupola time scale, which is in the order of 10 seconds. We have the particle settling time, which is on the order of 1, maybe 10 seconds. And these two slow processes, the falling particle and the relaxation of the cupola happening at the same time scale, they will lead to this vertigo. The fast processes actually do not matter that much. Now, this is all quite theoretical, and maybe it's more clear when I show you what this all looks like. This is a movie done from a master thesis by a student quite some years ago. He designed a scale-up model for a semicircular canal. Why scaled up? Well, if we want to study this, everything is very small, and so we decided to make it 5 times larger. We used Reynolds number scaling to adapt the viscosity of the fluid, the density of the particles, to make this semicircular canal, which is 5 times larger than in reality. And we mimic a motion, a typical motion of a person lying down in bed. And we have a particle down here, it's this red circle. And it was maybe a bit difficult to make out, but there's this latex tube inside the canal. No, sorry about this. I think whenever I use the laser pointer, it doesn't like it. Yeah, here you see this latex tube on the bottom left. Here, the latex tube. And in the movie, you will see the particle moving. Yeah, let's just look at the first case. Yeah, here's the latex tube up here. This is like the utricle, and this is a model for the cupola. We tilted the cupola by 90 degrees so we could read it out by a laser, by a vibrometer. And you can now see the particle sitting here, how it's falling down. Huh? It's falling down along the outer wall and getting slower and slower as it comes to the bottom. And as it is flowing down, it's dragging along the fluid. This is all scaled up, but in terms of time, this is pretty much what happens in reality. Now, let's look at the therapy. This is a typical maneuver that is being done to get rid of particles in one of these canals. Position one is called the Simon maneuver. So position one is here. When the patient sits on the bed, they tilt the head is to perfectly align, well, actually perfectly align this canal with the plane of motion. And then first, the doctor puts the patient down on the bed on the left ear, right? And then flips over the patient to the opposite side, to the right ear, and then back up. Rather simple if you know where the particle is sitting. And this maneuver is quite successful if you do it right. And there's a lot of debate, or was a lot of debate, how should you do it right? How fast should you do these movements? How long should you wait in these different positions? And yeah, essentially everyone tried out something and it was never really clear. So we actually used our model, the model that I just showed you, to study that. Essentially what we did, what we did is we changed the sequence, like the duration of waiting time. So on the left and right, you see the same maneuver, except that in one we wait for a long time between two movements, the other one we wait less. So it is the first movement on one ear to the left, okay? And the particles, well, I hope you can see anything here. Particle fell down. Now on the left-hand side, the patient was already being brought up after a few seconds, while on this side, the patient is still lying down, still waiting. On the opposite side, the particle is falling down to the left, back into the model of the cupola. The cannula has settled in the cupola, in the ampulla. On the right-hand side, the patient is still lying down. We wait for a long time, for 45 seconds, until the particle has reached its lowest position. Still takes a few seconds. Now it has reached its lowest point. And only now we put the patient back up. And what has happened now is that the particle has gone to the right-hand side of the apex and it's falling down on the right-hand side of the model. The right-hand side falling down here and falling into this U-tricle. That's exactly where you want to have the particle. So it's all about how long you wait between the maneuvers. And of course, you can test out like 45 seconds is certainly enough. And there's something in between. And we tried at different configurations. So unsuccessful Simon maneuver, no waiting time, successful long waiting time. So that was essentially what you can do with this type of model. So this is, I think it's in my last slide here. Yeah, this is the last slide I wanted to talk about. This is a different story. Maybe you remember that disease or the patient was sensitive to sound. Okay, look at the eye, it's tilting to the left. Whenever the tone is on, it's tilting to the left. Okay, so whenever the tone is on, the eye is tilting by a few degrees per second to the left. So obviously this person has a symptom called Tullio's phenomenon or Tullio's symptom. This is a sensory crosstalk between the hearing and the balance sense, right? Remember in the beginning, I told you about that it's kind of interesting that the hearing and the balance sense is in the same organ, right? They're communicating spaces. The fluid is the same fluid. And so somehow maybe it's not so surprising that there are illnesses, diseases, in which sound, which obviously creates a fluid flow in the cochlea, somehow also creates stimulation of the semicircular canals. Mathematically speaking, though, it's not so obvious, right? We have a relatively high frequency stimulation, right? This tone, and it was a few hundred hertz. So how can a few hundred hertz tone, how can it generate a flow which is directed, right? The directed flow. So somehow we need to have a mechanism to get from an oscillatory stimulation into a directed flow in a toroidal canal. And the solution to that, or the solution that we proposed, is that one here on the right-hand side. So what do we see here? It's a toroidal structure. It's filled with fluid, has no valves in it. So never mind about these dark structures here. This is an open torus, except that it has a relatively stiff plastic tube here and a rather soft section here, okay? And I hit this soft part of the tube with an oscillatory stimulation. So think of this like as the acoustic waves hitting at a certain frequency. Of course, it's not 200 hertz, but it's all quite larger, okay? So by hitting it in an oscillatory way, I can create a directed fluid flow. And actually by hitting it at different locations, I can even change the direction of the flow. Can either make it go in counterclockwise direction or in clockwise direction. This is called an impedance pump system. It's quite an interesting pump. It's not very efficient in terms of pumping efficiency, but it's quite cool because it really translates oscillatory stimulation into directed flow. And it has all to do with wave propagation, right? Arterial pulse propagation, remember that? We stimulate at one location, we get waves traveling in either direction. And we get reflections. No, I cannot stop it anymore. Okay. We get waves traveling in either direction and we have impedance jumps. Why? Well, we have a soft tube and a stiff tube. So here and at the two ends of the soft tube, we have wave reflections. So we get a lot of wave interference. And by hitting at the right place, the interference is such that we get a directed flow. So this is just showing you that there's a lot of really cool phenomena going on inside the inner ear. And this also explains, or maybe it doesn't completely explain, but to give you an idea how the semicircular canal and the cochlea can live next to each other unless there's some problems, which then leads to a sensory crosstalk where this timescale separation between what the cochlea is doing, namely sensing frequencies from roughly 20 hertz to 20 kilohertz, separates from the timescale operating range of the semicircular canal, which goes from 20, 30 seconds to about 10, 15 seconds sorry, to about viscous blocking about 0.02 seconds, which is about 50 hertz. Okay, so this closes this lecture. Closes also our discussion on the inner ear. Next week we go to the lymphatic system. Okay, so see you again next week. Bye bye.